Good morning, Professor Basil and fellow colleagues. My name is Ayman Aly, and today I will be discussing the introduction to slide bearings and lubrication. In order to fully understand today's topic, I will be explaining some introductory information regarding bearings and lubricants, the type of lubricants, liquid lubricants, the types of sliding bearings, the types of lubrication, and lastly, hydrodynamic lubrication. So first off, what are bearings? Bearings are machine elements designed to constrain relative motion and minimize friction between contacting surfaces through which a load is transmitted. Bearings come in all shapes and sizes and in a variety of examples, but today we'll be focusing on specifically sliding bearings and their subtopics. Now, what are lubricants? Any interposed substance minimizing friction within a bearing is considered as a lubricant. Although lubricants are usually liquid, they exist in all forms, including gas and solids. As stated before, lubricants exist in all three forms of liquid, gas, and solid. With the majority of focus landing on liquid lubricants, they will be explained and demonstrated in great detail in the next slide. For now, let's take a look at gas and solid lubricants. Gas lubricants consist of any type of pressurized air, including nitrogen and helium. While on the other hand, solid lubricants come in many forms, including graphite, Teflon, and boron nitride. Although very uncommon, gas and solid lubricants do come with their own advantages, which liquid lubricants do not possess. They are both resilient in terms of temperature change, while liquid lubricants are subjected to freeze in low temperature and evaporation in high temperature. They are also resilient to high speeds with a low coefficient of friction, unlike liquid lubricants. Now, liquid lubricants. Being one of the most commonly used lubricants in today's day, liquid lubricants consist of approximately 90% oil and 10% additives. What are additives, you might ask? Liquid lubricants that are oils are characterized by their special properties such as viscosity and given specific names designated to said properties. This is where the additives come in. There are many types of lubricants, therefore many types of additives. Some of the common additives include pour-point depressants, which cause the oil to flow better at lower temperatures. Another type is viscosity index improvers, which have less variations of viscosity with given temperatures. We also have defoamants, which are used to resist foaming when agitated in high-speed machinery. Oxidation inhibitors resist oxidation at high temperatures. Corrosion inhibitors prevent corrosion of metal surfaces. Detergent and dispersants minimize the formation of engine deposits. And lastly, anti-wear additives reduce friction and wear. We also have one more subtopic, which is called greases. Greases are thickened liquid lubricants that provide special properties as stated above. They are usually used when the lubricant is required to be stationary, and in most cases when frequent lubrication is either difficult or costly, thus making it time and cost effective. They also prevent harmful contaminants from entering between bearing surfaces. Now, with greases holding all these advantages, they cannot circulate, thus cannot serve a cooling and cleaning function, deeming them unused. Now, slide bearings, also known as plain bearings, require the light sliding of the load carrying member on its support rather than the rolling element bearing that have balls and rollers between the surfaces. There are usually thin shells that are easily replaced, providing bearing surfaces for materials such as bronze and babbitt. Sliding bearings can either be split or made as a one-piece cylindrical shell, also known as a bushing. Now, there are two types of sliding bearings. The first being journal bearings. Journal bearings, also known as sleeve bearings, are cylindrical and support radial loads. On the other hand, the second type of sliding bearing is thrust bearings. Thrust bearings are usually flat and support loads within the same direction as the shaft axis or opening. Now, back to lubrication. Lubrication can be defined according to the degree of separation regarding the sliding surfaces. There are specifically three cases of lubrication. The first case is hydrodynamic lubrication. During hydrodynamic lubrication, the surfaces are completely separated, thus no contact at all, due to the lubricant film, which results in no surface wear at all. The typical film thickness resides between 0.008 to 0.020 millimeters. Due to no contact at all, friction is originated from the lubricant film and is typically very low with a value of 0.002 to 0.010. This will further be explained in great detail within the next slide. The second case is mixed film lubrication. In this case, the surface peaks are intermittently in contact, resulting in mild surface wear. This will also lead to an increase within the coefficient of friction between 0.004 to 0.1. Lastly, the third case is boundary lubrication, where the surface peaks are continuously and extensively in contact, which typically would result in high amounts of friction, but the lubricant reduces the friction, resulting to minor surface wear, with the coefficient of friction increasing between 0.05 to 0.2. Now, onto the basics of hydrodynamic lubrication. To make it simple and understandable, it's best explained through the diagrams shown below. The top and right diagrams are a realistic preview of what a loaded journal bearing with an oiled-filled clearance looks like. Now, with regards to the three diagrams to the left, in Figure A, the journal bearing is at rest. When the shaft starts to continuously and slowly rotate clockwise, the shaft will roll to the right and stay in that current position due to the slow rotation speed, which is seen in Figure B. This is referred to as boundary lubrication. When the shaft rotating speed is significantly increased, pressure also increases, thus causing the shaft to float, which is shown in Figure C. This is referred to as hydrodynamic lubrication, where a minimum film thickness, H node, is formed. To dive deeper into hydrodynamic lubrication, we must take a look at the three basic parameters that influence the said lubrication and its coefficient of friction. All three parameters affect each other and play a major part within the bearing. The first parameter is viscosity, given by the symbol mu. The higher the lubricant's viscosity, the lower the rotating speed needed for the shaft to float. An increase in viscosity also produces more bearing friction. Now the second parameter includes the rotating speed, given by the symbol n. The higher the rotating speed, the lower the viscosity needed for the shaft to float. Also, an increase in rotation speed will also result in more bearing friction. Lastly, the third parameter includes the bearing unit load, given by the symbol P, which is better known as the load W divided by the bearing projection area L times D. The smaller the bearing unit, the lower rotation speed and viscosity needed for the shaft to float. A decrease in the bearing unit load will result in more bearing friction. Now, the pre-requirements needed to achieve hydrodynamic lubrication include relative motion of the surfaces, wedging actions such as the shaft eccentricity, and the presence of a suitable fluid. Finally, for a quick example, let's take a look at an engine crankshaft. The engine starts off at rest. When being cranked, it starts to slowly turn, producing boundary lubrication. When the engine starts, the combustion increases the rotation speed significantly to establish hydrodynamic lubrication. Thank you very much, Professor Balzo and my fellow colleagues, for your attention, and I hope you now have a deeper understanding on the introduction to slide bearings and lubrication. Have a good night.